Hello, ladies and gentlemen. Are you ready for the last session today? Okay. The last session is, we will have a party. Brief introduction to multi-party computation, MPC, which will be delivered by our honorable speaker, Dr. Ivan Tjuawinata from Nanyang Technological University. Let's give him an applause.
Okay, thank you. Okay, so for the next session, I will briefly introduce the concept of multi-party computation, or MPC. So intuitively, what we want here is that we want to be able to compute some function, but we want all the inputs to be private. We don't want to share the input, but we want to compute the output. Okay, so this is the overview of this session. First, I will discuss some history and motivations of MPC by giving you some examples where it can be used. Next, I will give some definitions of MPC, and then I will focus on the MPC that is based on secret sharing scheme. And in this MPC, the main problem is how to conduct multiplication. So in here, we will discuss 3 different methods to multiply, and lastly, I will give an example for the whole thing. Okay, so some history about secure MPC. So MPC was first introduced by Yao in 1982, and this is introduced through this problem, Millionaire Problem. So suppose that you have, there's 2 millionaires, and they want to compare to know which one is richer, but of course they don't want to share their wealth to the other. So in fact, Yao provided this problem and also the solution to it, and this one later becomes known as Yao's coupled circuit. So this problem was later generalized to n-party by these 3 people. And secure MPC is actually one of the most important primitives because almost all distributed secure protocols can be based on secure MPC. Okay, so I will give you 2 examples. Okay, first of all, suppose that there's a boy and a girl, and they have some feeling towards each other, and they want to know whether they should go on a date or not. But of course, in this case, suppose that one of them is not interested in the other, then the other should not be able to learn what is the feeling of the other person. Yeah, so the main question is how to decide whether there's a mutual interest. In other words, whether we can calculate x1 times x2. Okay, so this one is the formulation of the same problem, but mathematically. Suppose that you have a boy, Bob, and a girl, Alice, and they have this feeling towards each other. So for example, this xp is 1 if they are if Bob is interested to Alice and 0 otherwise. So they want to know what is xa times xp, and they want to know if it is 1 or not. But the main requirement here is that if xa is 0, then Bob should not be able, Alice should not be able to learn what is xp, and vice versa. Okay, so one way, this is the ideal solution. The ideal means that it is in the ideal world. If they have a mutual friend, then they can simply tell this mutual friend the feeling. And knowing xp and xa, then this third person can just simply announce what is xa times xp. Okay, so now the main question is, can we do similar things but without the existence of this third person? Okay, so let's consider another example, sum of salary. Suppose that there's 5 friends and they have their own salary. And they want to know what is the sum, but they don't want to tell the others what is their salary. So can they find x1 plus x2 up to x5 without telling each other what is their salary? So please take note that in here, this problem is only meaningful if there's at least 3 friends, because as you imagine, if there's only 2 of them and they know the sum and they know their own salary, it's trivial to know what is the other salary. So we will just assume that n is larger than 2, and we will discuss two solutions. One is with trusted party like before, the other is without this trusted party. Okay, so for trusted party, it is very simple. It is very similar to before, where there's the 6th person, and everyone just tell this 6th person their salary. And without revealing anything, this 6th person just announce the sum. So this is quite simple. So the question is, can we do this without this 6th person? Turns out we can, and it's actually also quite simple. I'll skip the word here, just go back to the illustration. Like before, we still have x1 to x5, and now the first party, which is this one, thinks of one random number r. Notice that in here, since this r is only known to the first person, if the first person just tells the second person this r plus x1, the second person does not know anything. And the same thing, since this s1 is not known to the third person, then he can just add this x2 to this s1. And we can do this again and again until this s5 is back to the first person. Now the first person, knowing this and knowing r, he can simply announce s5 minus r to be the sum. Now take note that in here, if everyone is behaving honestly, no problem. However, imagine that if the first person and the third person has some collision and they just share information. So remember that for S1, he knows r plus x1, and the third party knows s1 plus x2. So if they can work together, then they can simply, since they know s2 and s1, they can simply minus s1 from s2, and this coalition will know the salary of x2. So this gives us some intuition on the existence of some adversary. Okay, so given this example, you can see the use of this multi-party computation, and it is actually possible to do it. So in general, we have n parties, p1 to pn, and they want to compute some function fx1 to xn, such that xi is only known by pi, and he does not want to share this xi to anyone. So we want to have this concept of securely. So what is securely? Remember that from before, in the ideal world, if there's an n plus 1 trusted party, then everyone can simply just send this xi to this trusted party, and he can compute this f for them and just announce. So this one is what we want to achieve. So please take note that in here, we are not claiming that no information is leaked, because knowing the value of this fx1 to xn may give you some information about some private value xi. So for example, like I mentioned before, if there's only two of them and they just try to calculate x1 plus x2, no matter how you calculate it, if you know x1 and you know f of x1, x2, it's trivial to know x2. So intuitively, like before, we will use simulation-based security, where we want to make sure that our scheme without any trusted party is indistinguishable from the scheme with this trusted party. So this gives us a concept of adversary that controls some party, and then he can try to gain more information from what he is allowed to. So some assumption here. So first of all, we can try to assume what is the computation ability of this adversary. Either he can only do polynomial number of operation, or he can do as big as possible. Next, we can also try to assume how many parties can be corrupted, and usually we will denote this by T. And lastly, there's two different control of this adversary to the corrupted party, passive or active. So in the passive, he's just trying to gain information without changing anything from the input. However, for active, he can change the response of each of the corrupted party, and this one will make the calculation wrong. So for some scheme, it can claim to be secure even under active adversary. Okay, so there are many techniques to build this MPC. We have heard the first two, secret sharing scheme and homomorphic encryption. There's also these two, oblivious transfer, which was described earlier by the previous speaker, and also Yau's couple circuit, which is the solution of the first MPC problem. In this talk, I will just focus on secret sharing scheme. You may ask, why sharing scheme? Actually, it has several advantages. First, it is computationally much more efficient because in here we just do calculation plus and times. We don't have any public key crypto system which is relatively more expensive. And because of this, using this secret sharing scheme, actually it can provide unconditionally secure MPC scheme. So in other words, we don't care how many calculations the adversary can do, it is still secure. And he will not learn anything about the information he is not supposed to learn. Okay, so you may remember from the talk yesterday that there's a lot of possible secret sharing scheme protocol. In here, I will just use two examples. First of all is the N out of N secret sharing scheme, in which having N parties and a dealer D, and he wants to share this private value V. What we want is when all of them gather together, then they can recover V. But any groups that has less than N parties does not learn anything about this V. So one way to do this is simply for the D to randomly take N minus 1 value, V1 to Vn minus 1, and then let Vn to be V minus all of this. Notice that in here, if I only have N minus 1 values, I still don't know anything about V. So this is called additively shared. Another one is Tn threshold secret sharing scheme, which is a relaxation of N out of N. In here, instead of requiring N of them together to have the ability to recover V, we only require that if there's T plus 1 party, it is enough. And if there's T, they learn nothing. And you may remember from yesterday that one of the examples is Xiaomi secret sharing scheme. And again, this is just some intuition on it. You may, if you have a polynomial of degree T and you don't know the coefficient, if you know the value of this polynomial at T plus 1 different points, then of course you can use interpolation to find what is F. However, if you don't, then you don't know anything about the coefficient. Unless you know F0, then you know the constant. So intuitively, you may remember that for Xiaomi secret sharing scheme, what we do is just let the secret value V to be F0 for some randomly generated Fx of degree T, and then we agree on this alpha 1 to alpha n, alpha I for player I, and then the share of party Pi is simply F alpha I. Now, you may observe that actually this one has a lot of relation with Reed-Solomon code, because if you have this Fx and then you just put all the shares as a vector, then this is simply just a code word of Reed-Solomon code. This observation actually we will use in the later analysis about the active adversary. Okay, so one observation that we can see from both secret sharing scheme is that they are linear, in the sense that if we have V1 to Vn to be the share of V, and W is shared to W1 to Wn, and if we have this C in FQ, then if we just add the shares V1 plus W1, V2 plus W2, and so on, this is just the share of this V plus W. If I multiply each of the share by C, then this one is the secret value of CV. And lastly, if I just ask the first person to add C and all the other just kept the same, this is the secret value, the share of secret value of C plus V. So actually, this observation is one of the main points of why we can build an MPC based on secret sharing scheme. Okay, so now let's try to build. Like before, we have n parties, P1 to Pn, and Pi holds this xi, and they want to calculate this f x1 to xn, where f is known to all. For simplicity, let's assume that it's only generated, it only consists of addition and multiplication. So for example, we will not be able to have this XOR, selection, comparison, max, and so on. So in fact, this is one of the limitation of secret sharing based MPC. We mainly focus first on this addition and multiplication. Okay, so before performing this calculation, first they just need to choose one secret sharing scheme, either the n out of n or Siamese secret sharing scheme. And they use this to secretly share this xi. Now, they can choose any one of them, but once one of them choose, then all the other needs to use the same choice. Furthermore, if they use this Siamese secret sharing scheme, then the choice of alpha 1 to alpha n needs to be the same throughout the computation. Now, for each step of calculation, this is what we want. First, the input needs to be either public or it is secretly shared using this method that I mentioned earlier. Unless it is the final result, we don't want to reveal what is the value because this one may leak some information. And lastly, due to this linearity that we observed earlier, actually for addition by constant and multiplication by constant, this is easy. We just use the property earlier and it can be calculated locally. We don't need any communication between the parties. So the remaining question is, if you have two shared value u and v, how to calculate the shares of this u times v? Remember that in here we don't necessarily want this value uv to be refilled. We just want it to be shared. Okay, there are several techniques: replication scheme, pivot triple, and the sharing method. So for replication scheme, it works generally on additive secret sharing scheme only. For pivot triple, it can be applied to both, and the sharing method it is used for Siamese secret sharing for now. Okay, so let's start with this, what we want to do. So recall that the value of u and v in FQ, if it is additively shared among n parties, then Pi holds ui and vi, such that the sum of ui is u, sum of vi is v, and what we want is this wi, such that Pi holds wi and the sum of wi equals to u times v. And we want to do this without leaking additional information. And even if we need external party, we don't want him to be required to be online throughout the entire calculation, and if possible, we don't want him to be trusted because it's harder to find a trusted third party. Okay, so let's consider the application method. So remember that now you have u equals to sum of ui and v equals to sum of vi. So if you just expand everything, you will get uv equals to this one. Now note that in here for the term for the first summation ui vi, this one can be calculated by Pi without doing any interaction. So we just ask Pi to calculate ui times vi. So the remaining question, we can just combine them together to just ask this one. If for I not equal to j, how to calculate ui times vj? So this one can again be reduced to just this question. If you have two parties, A and B, A holds x, B holds y, how to calculate the share of x times y? And now, for replication method, we assume they employ the help of an external party C that is not always online and he's not also trusted. So, for this one, A randomly choose x1 and x2 and set x3 to be x minus x1 minus x2. So in other words, A just additively shared this x to A, B, and C. The same for B, but it's a bit different because now it's not that x1 is for player 1, x2 is for party 2, but now A holds only x1, x2, x3, and y that is not y1. B holds everything except x2, and C holds this 2. So remember that this one means that for A to learn what is the value of x times y, he just needs to learn what is y1. And for B to learn what is x times y, he just needs to learn what is x2. So the whole method, we want to make sure that this does not happen. So we must always hide what is x1 from, what is y1 from A and what is x2 from B. So we can just calculate like before, xy equals to this one, which gives us this 9 value. Okay, so I just put this 9 value in a 3 by 3 matrix, and we just decide, now we try to find out what does each party know and what does each party need to calculate. Okay, so first of all for A, he knows this x1, y, so he knows this 6, which is this second and third column, and out of this 6, we just ask A to compute this 3. For B, he knows the first row and the last row, so he can calculate this 1, 2, and 3. And lastly, for C, he knows this 4, so of course, since we just have these 3 left, we just ask C to compute this one. Now notice that in here, everyone can compute their own share. Furthermore, Z1 plus Z2 plus Z3 is just all these 9 terms, which is simply U times X times Y. Okay, so this is good. However, the question is, how can C send this Z3 back to A and B? So first alternative, if Z3 is directly sent to A, then she can simply compute Y1 from this formula. So in other words, if A knows Z3, A knows everything, so we don't want to do this. Similarly for B, if B learns Z3, then he can learn X2, and remember that this X2 should be the only thing that is hidden from B. So both alternative does not work, but we want this Z3 to be transferred back to A and B because C, we don't want C to always be online. So we can just simply additively share it again one more time. So we just pick R and just send R to A, Z3 to B. And this one will give A, Z1 plus RB, Z2 plus Z3 minus R. And this one solves the problem. Now, notice that in here, we just stop at this share and we don't publish the share to get back what is X times Y, because unless it is the final result, we don't want this to be refilled. Okay, before I go to the second method, any question for the first? Okay, for the second method, this before triple, in here, the main advantage is during the calculation of the actual function, we don't need any external party. However, we will need some pre-processing phase where they meet, let's say, overnight or the previous day to just calculate some values that can help in the calculation. So like before, suppose that we have two shared values U and V, where Pi holds Ui and Vi, and we want to calculate W1 to Wn, where Wi is held by Pi, and the sum of it equals to UV. So assume for simplicity, although this preferred triple works for both additively shared and Siamese secret sharing scheme based, let's just make it easy and assume that it is additively shared. Please take note that everything that I discussed here also works for Siamese secret sharing based MPC. Now, as I mentioned before, suppose that overnight or during weekends, this n party gather without knowing what is x1 to xn and generate this A, B, C such that C equals to A times B, but none of them knows what is A and C. So Pi only knows AI, Pi, and Ci, and such that the sum of A is A, sum of Ci is B, and sum of Ci is C. So note that up to this point, no one knows what is A, P, and C. So this triple APC is called preferred triple. So let's see how can we use this to calculate U times V. Okay, so this is the method. So first of all, it may look a bit strange because now first they calculate delta I, which is Ui minus Ai, and gamma I, which is Vi minus Pi. Next, they broadcast this so everyone will know what is delta 1 to delta n, gamma 1 to gamma n. And notice that in here, by definition, sum of delta I equals to sum of Ui minus sum of Ai. Okay, so now everyone knows this value U minus A and V minus B. And please take note that now these two are public. Now, notice that in here, if Pi holds this W1 equals to U1 comma plus. Okay, so now after we ask all the n players to calculate this one, we claim that actually this Wi's satisfy this one. So let's try to calculate. So sum of Wi, this one will give us sum of Ui times gamma. Okay, so if you open everything, you will get this one, and you can see that everything got cancelled. And you will get UV plus C minus AP. But we know C equals to AP, so again, this one cancelled to get us UV. So this is the proof why this method works. So now we have this sum of Wi to be equal to U times V. And note that in here we don't really discuss how to generate this APC triple. This one will be skipped. The only thing that we, maybe briefly I can give you how to generate this one. We can simply use the previous replication method in the offline phase to generate this A, P, and C. So in here, now we can change that the trusted, the external party still not trusted, and now he does not have to be online during the actual computation. It's just during the offline phase. Okay, so any question before we move on? Okay, lastly, resharing. Suppose that now, again, like before, we have U and V shared, but now we use the Xiaomi secret sharing scheme, and we use this polynomial FU and FV. So by assumption, this one is what is FU and FV. And notice that in here, if you multiply FU and FV, Actually, the constant is still u times v. But now, to interpolate this p, actually you will need 2t plus 1 party instead of just 2t. So, of course, we don't want to do this because if, for example, we just have a lot of calculation, a lot of multiplication, then your interpolation will need much more party, and up to some point, this number may be larger than n, which is impossible for us to do. Furthermore, notice that in here for px, for any player pi, he can learn p alpha I. And now for all of this, if we make into a system of linear equation and get as a matrix, you have this equation. Notice that in here, this one is known to any party, this one is unknown, and we want this uv, and this vector p alpha 1 is known by t1, p alpha 2 is known by party 2, and so on. So let's denote this by a times p equals to p. Notice that in here, if 2t is less than or equal to n, then we can find some lambda such that lambda times a equals to 1, 0, 0, 0. And the good thing of this is that if we multiply lambda from the left for both sides, then we will get uv equals to lambda times this one. But of course, this one is known for everyone, so now there is a way to calculate uv. Please take note that in here, although everyone knows lambda, we cannot just ask each player to calculate lambda I to times p alpha I and then just publish, because remember, we do not want to reveal uv, we just want to reveal the shares. So what we can do is just reshare it again, p alpha I reshare using this hi, and suppose that now the share for our player pj is hij. Never mind, just draw. Okay, so like before, we have this p alpha I to be shared by using this hix, and the share of pi, so the share of pj supposed to be hij. And remember that uv equals to lambda times p alpha 1, p alpha n. So now, since we have this hij, then notice if there are t plus 1 parties, then from hij, from this hij for any I, we can recover hix, which gives us this p alpha I. So in other words, using the linearity again, this sum can get us the sum of lambda I p alpha I, but we know that this one is again uv. So because of this, based on this hij, we can conclude that wj should be this sum. Okay, so this is for the resharing method. Notice that in here, we will use the resharing, and after that, we just use the linearity again to be able to find the shares for this U times V. Okay, so what about active adversary? So remember that up to now, we just assumed that everyone behaved honestly. But now, if it is active, that means that for these T parties, they can lie, and that means that we can assume that there's at least T shares that is wrong. Now, notice that if we use Siamese secret sharing scheme, we use a polynomial of fx of degree T such that f0 equals to secret S, and then we have this n distinct value alpha I such that pi holds f alpha I. Now, having T corrupt shares, again, if we move to the Litt-Solomon code way of seeing it, then this one is simply a code word with error of having weight T, or at most T. And remember, we can, since it is MTS, that means that the minimum distance is n minus T plus 1, and we can correct error up to the minimum distance minus 1 over 2. So, the scheme will still be secure as long as this T is less than or equal to n minus T over 2. So in other words, here T is less than or equal to n over 3. So this tells us that if you are using Siamese secret sharing based MPC to calculate this plus n multiplication, you can be secure against active adversary, and even you can correct the result of the calculation as long as the adversary only control up to n over 3 of the party. Any questions? Okay, so let's end with the example. Suppose that now we have only 3 parties, P1, P2, P3, such that Xi is in F11. So remember that this means that everything is only from 0 to 11, and all the operation is done modulo 11. And let's take X1 is 2, X2 is 3, X3 is 4, and they want to calculate this one. So as I mentioned before, if we want to use additive secret sharing scheme with pivot triple, then we need to share it using additive secret sharing scheme first. So suppose that now for player 1, he shared this X1 using 4, 6, 3. So this means that player 1 received 4, party 2 receives 6, party 3 receives 3, and the same thing for X2 and X3. So you can check here that 4 plus 6 plus 3 is indeed 2, 2 plus 10 plus 2 is indeed 3, and 1 plus 3 plus 0 is indeed 4. Again, modulo 11. Furthermore, notice that here we have a multiplication, so we need a pivot triple. So let's use APC such that this one is the A, B, and C. So you can notice that A is 5, B is 18, 7. So 5, B is 7, and C should be 2, which is 5 times 7. Okay, so now let's cut this into 2, x1 times x2 and 5 times x3. So by linearity, we can simply calculate y2 by asking everyone to calculate 5 times x3. So P1 will receive 5 for the share of y2, P2 will receive 4, and P3 will receive 0. So y2 is shared to 5, 4, and 0. Again, if you want, you can check that 5 times 4 is indeed 9. Now for y1, it's a bit different because we need to use this pivot triple. So since the calculation, we have proved the correctness of calculation there, I just go quickly here. So you have delta and gamma to be 332 and 016, and then publish to get what is delta and gamma, which is 8 and 7. Then calculate for party 1, calculate this one. And party I also calculate the same thing as before. So now for Y1, it is 773. Again, you can check that 2 times 3 should be 6. This is 14 plus 3 is 17 minus 11 is 6. Okay, so now we already have the correct share of Y1 and Y2. We can simply add them together to get Y. This is 103. Now, after we have everything here, then all the parties can simply publish their share, 1, 0, and 3, and then they can recover this Y equals to 4. Any questions? Okay, if not, then that's all that I want to say. Thank you.
Thank you very much, Dr. Ivan Tjuawinata from Nanyang Technological University for the lecture on multi-party computations. Please stay a while on the stage. May I invite Dr. Al Suciana to come to the stage and hand over the souvenir to the speaker. Please give a big applause, Dr. Ivan. To me. Also to me. Okay, thank you very much. Well, ladies and gentlemen, this is the end of our agenda. After this, you can go home, take a rest, but please prepare yourself for the last 3 days of the summer course. We hope that you get many advantage of this event, make a lot of friends, and most importantly, we expect you to be strongly motivated to do further studies in cryptography. I am Konita, thank you for your participation, see you tomorrow. Announcement to all participants who attended the excursion last Saturday, please sign on the registration table before leaving this room. Thank you.